Okay, so another area problem here. This time we want the area inside the limacon, and that's going to be the red graph down below, and outside the circle, r equals 3. So inside the limacon, outside the circle. So we are talking about, well, why don't I highlight it? We are talking about this region right here. So this Pac-Man looking region here. Now the first thing I notice, there's symmetry here. So if I can just find this area here, I know that all I have to do is double it to get the entire area. So it's 2 times 1/2 times an integral, yet to be determined, d theta. So what I first have to do is think about, or what we have to first do is think about, let's say draw some theta lines here. And in doing so, we realize that we're hitting the circle first, and then the limacon is the last thing to be hit. And that seems to happen until, oh, look, a point of intersection. Okay, so starting at theta equals 0, we're definitely going up to something. Now, it's basically the area. So imagine the circle wasn't there. We could find the area of the entire limacon, but then we had to subtract off the area that's inside the circle. So it's going to be limacon squared, so 5 plus 4 cosine theta squared minus 3 squared. So all we have to do is figure out that upper limit for theta, and you can use a graphing utility if you want to. I'm just going to go ahead and solve the equation analytically here. So I'm going to set the r's equal to each other to figure out the values of theta where the r's are equal. So first thing I'll do is subtract 5 and divide by 4. Well, 3 minus 5 is -2, divided by 4 is -1/2. So where is cosine of theta equal to -1/2? Well, we know that that must occur in quadrant 2 or quadrant 3. And if my cosine is -1/2, that's a special angle, that should be pi over 3, 60 degrees. Because that's the angle that's opposite, the square root of 3, not the square root of 6. So that means that this entire angle here is 2 pi over 3. So that is the story right there. So there's the setup of our integral. So let's figure out the rest of it. So these cross out, so I'm not even going to bother writing a number anymore. So we're going to have the integral from 0 to 2 pi over 3, 25 plus 40 cosine theta, plus 16 cosine squared theta, minus 9. Okay, just squaring the binomial and then subtracting 9. So then to pull it all together, 25 minus 9 is 16. And then we have 16 times the substitution for the double angle identity. Or power reducing identity, I guess is what it's typically called. It could be called anything, really. So then multiplying that out and simplifying. So you have 16 here, we have 16 times 1/2 there. So that's going to be 24 plus 40 cosine theta. And then we have 16 over 2 is 8 cosine of 2 theta. And that's 0 to 2 pi over 3. And now we're ready to integrate. So we have 24 theta plus 40 sine theta plus, when I integrate cosine 2 theta, it's sine of 2 theta. But then I end up dividing by 2, so that's going to leave that to be a 4. So here we go. So we have 24 times 2 pi over 3 plus 40 sine of 2 pi over 3 plus 4 sine of 4 pi over 3. And then we plug in 0, we're going to get zeros across the board there. So 24 times 2 pi over 3 looks like it's 16 pi. Sine of 2 pi over 3, well, that's quadrant 2. That's root 3 over 2. So that means this is plus 20 root 3. And 4 sine of 4 pi over 3, well, that's going to be negative root 3 over 2. So 4 times that would be minus 2 root 3. So the final answer should be 16 pi plus 18 root 3. So the hardest part is getting it set up. Once you have it set up, it's just the same old integration techniques, mostly using those power reducing formulas, and then just keeping track of the fine detail. When you're dealing with angles like pi over 2 or pi, those are easier because cosine and sine of those are either 1 or 0. But when you're starting to use different angles, that's when our answers can get a little bit more interesting. So hopefully that helps, and thanks for watching.